In this fork are also, you can use the word dining philosopher. There is a kind of problem is occur like deadlock problem. In this problem, every philosopher need a fork, but if they access or they follow the kind of instructions, then still one person is remaining for acquire the fork. In the starvation condition, allow them only 2% to access the forks and other should remain in waiting, and after releasing them they are allowed to access in that situation. Number of philosophers is there 5, and I philosopher number is 0 to 4 is initialized. Now number of thinking philosopher is thinking called the function, and fork I accessing the number of forks, and allow only 2 persons for accessing the fork. They are allow them to eat, and then again allow after releasing them put the right fork back on the table and left fork back on the table. This sequence is followed. A known solution to the dynamic philosopher problem. Dynamic philosopher come into the next situation where number of philosopher representing as 5, number of I left neighbor is n, which is calculating with the modulus, and these steps are need to follow for completion their problem. But in the same manner there is a kind of problem occur like mutual exclusion, and you can say acquiring problem and forks accessing at the same time. Solution to dynamic philosopher problem is allow 2 of them for accessing and another should wait. A barber shop consists of a waiting. This is another problem that can you say the sleeping barber problem. A barber shop consists of a waiting room with chairs and the barber room containing the barber chair. If there are no customer to be served, the barber goes to sleep. If a customer enters the barber shop and all chairs are occupied, then the customer leaves the shop. If the barber is busy but chairs are available, then the customer sit in one of the free chair. If the barber is asleep, the customer wake up the barber. In both cases, barber we want to make busy and we want to utilize his efforts in this system. If all the chairs empty, then and barber can sleep, and if all the chairs are busy and the customer is coming, then he leave out from there. So the sleeping barber, if number of chairs are available, we have to apply the condition for exiting the consumer when the all chairs are full and barber is busy. And another case when the condition is satisfied and consumer is satisfied after their job, then he can leave from that shop. Then the next topic is locks. In this, locks are another synchronization mechanism. A lock has got 2 atomic operations similar to semaphore to provide mutual exclusion. These 2 operations are acquire and release. These operations should be followed for acquiring the lock or for storing the data. After storing the data, we need to acquire lock, and after locking that particular data or that particular task, if we want to access that, then we have to again acquire lock and then release that particular lock after acquiring for storing and accessing the data. These are the situation: lock acquire, then enter into the critical section, then lock release. This is the sequence is followed for accessing the data by the number of processes. The difference between a lock and a semaphore is that a lock is released only by the process that have acquired it earlier. Which one acquired the resource or lock earlier have to release that particular lock at first. Next is monitors and condition variables. Monitors and condition variables problem, or in this topic, a concurrent programming, a monetary synchronization construct that allow thread to have both mutual exclusion and the ability to wait for a certain condition to become true. In this case, number of processes are there for execution and for completion their task. If number of processes are executing their task, then the another process have to wait, and they are able to wait or allow them to wait for accessing the data, for accessing the resource or system. In that case, we have two conditions. A condition variable is a basically container of a thread that are waiting on a certain condition. Monitor provide a mechanism for thread to temporarily give up exclusive access in order to wait for some condition to be met before regaining exclusive access and resuming their task is required. If we want to access the data, then we require the exclusive access. If we want to release that particular system or particular data, we have to allow to another process to enter the system. And the next topic is deadlock. In this, we have some conditions as like mutual exclusion condition, hold and wait condition, no primitive condition, and circular wait condition. These all conditions are for the situation where deadlock occur and deadlock is existing into the system. If we want to prevent our system to enter the deadlock situation, we have to prevent our system to enter any one of these conditions, which are the characteristic of deadlock. Now come to the topic types of resources. Preemptible resources. These resources can be taken away from the process with no will effect. Memory is an example of a preemptible resources. And the next is non-preemptible resources. This resource cannot be taken away from the process without causing will effect. For example, CD resources are not preemptible at an arbitrary moment. Preemptible resources are resources which are acquired by a system and exiting system on the requirement, and non-preemptible resources are the resources which hold by a process but not getting released that particular resource after completion their task, or continuous retaining that kind of resource for a longer term. This may cause the problem of deadlock. In deadlock, there is a permanent blocking of a set of processes that either compete for system resource or communicating with each other. Deadlock is a situation when we have the number of processes in execution state and every process requesting for another process by retaining the existing resource, and every process getting busy in execution their task, but they are requesting for that process which is held by another process and not going to release the existing resource which is held by them. So there is every process is waiting for another process, which is every process retaining the resource which is held by another process. No efficient solution is there for preventing that situation. Involve conflicting needs for resources by two or more processes. So the conditions are: first, mutual exclusion. In this situation, only one process may use a resource at a time. The resource involved are non-shareable. The next is hold and wait. In this, a process requests all of its required resources at one time. And the next condition is no permission. If a process holding certain resource is defined or denied a further request, that process must release its original resource. If a process requests a resource that is currently held by another process, the operating system may preempt the second process and require it to release its resource. The next condition is circular wait, prevented by defining a linear ordering of resource types. In this problem, a resource is held by a single process, but it is requesting for another resource which is held by another process, and this thing is happening between more than 2 and more than n number of processes. So the circular waiting condition is occurred at the time. So we have to manage kind of problems, like example is there traffic deadlock. In that case we have the number of ways, and you can say there is the 4-way, east, west, north, south, and the traffic is coming from all directions at the same time. So in that situation the traffic is get choked and nobody is able to move and go further. That kind of situation we can say the deadlock situation. In the other way, the deadlock can be possible if the number of vehicles entering into the particular way or entering into the particular deadlock condition is not allowing anybody to go out or exit from that way, and they are continuous entering into the queue and not going to release the way to allow any other traffic from the other direction. These are the illustrations of deadlock. Now come to traffic deadlock. Mutual exclusion condition applies since only one vehicle can be on a section of the street at a time. And the next is hold and wait condition applies since each vehicle is occupying a section of the street and waiting to move on to the next section of the street. The next one, no primitive condition applies since a section of the street that is occupied by a vehicle cannot be taken away from it. And the next is circular wait condition, which is very much popular in deadlock condition, applies since each vehicle is waiting for the next vehicle to move, that is each vehicle in the traffic is waiting for a section of the street held by the next vehicle in the traffic. These condition you can say the characteristic or you can say the causes of deadlock. If we are able and if we able to remove any kind of this problem, so we are able to remove the deadlock condition. And this is also the example of deadlock where the number of progresses are there, like get B, get A are the request and required by the resources, and if anybody is going to release, and there is also mentioned the number of release progresses and processes. If every process requesting for another resource and not going to release existing resource which is held by it, so the deadlock condition possibly will occur in that situation. If we want to deadlock is not occurred into the system or into that scenario, so we have to make some space, we have to make some situation where any one of these condition will not occur. If we able to remove any one condition from the given conditions, then we are able to remove the deadlock condition from the system. So next topic is resource allocation graph. Resource allocation graph is a graph in which deadlock can be described through a resource allocation or through a diagrammatic form by using number of processes for represent as P1, P2, and for representing resources we are using R1, R2. As in such situation, a directed edge from a process to a resource implies that Pi has requested for Rj resources. A directed edge from a resource to process Rj implies Pi, implies that Rj has been allocated by Pi, means Rj resource allocated by or allocated to Pi. If Pi implies Rj, means process Pi requesting for Rj resource. If the graph has no cycle, deadlock cannot exist. If the graph has a cycle, deadlock may exist into the system. So this is the graphical notation of resource allocation graph. In the first notation, there is the number of processes are there as like P1, P2 and P3. Same way, there is number of resources are there R1, R2, R3, and the R1 having the number of dots, which is having the number of resource representing the number of resources are there. So there is P1 implies R1 means P1 allowed to access by R1. R1 implies P2 means R1 resource held by P2. P2 implies R3 means P2 requesting for accessing in R3, and R3 implies P3 means R3 resource is held by P3 process, means every resource is held by another process and requesting for another resource. So this is the condition of deadlock. In the same way, the resource allocation graph in the next diagram, resource allocation graph with the A deadlock. In this situation, we having P1, P2, P3 and P4 resources, and we have only 4 resources or 2 blocks R1 and R2. R2 resource requested by P1 and same R2 resource have by held by P4 resource, and R2 resource requesting by P3 and holded by P1. Same way, P1 requesting for R1 resource and holded that resource by P2 and P3. So every process requesting for another resource and holding a single resource, you can say every process requesting for a new resource and holding the previous resource, not releasing the existing resource, it may cause the deadlock condition. And you can see there is a loop is occurring, or you can see the cycle is occurring in the both diagram notation or graph notations of resource allocation. Now dealing with deadlock situation, for prevention, disallow one of the 3 necessary conditions of deadlock occurrence. If we are able to do this, we can prevent our system to enter into the deadlock condition. Deadlock avoidance. Do not grant a resource request if this allocation might lead to deadlock. If any process requesting for such resource which may cause the error and which may cause the occurrence of deadlock, so do not allow that kind of resource to access or acquired for particular process. Now come to the next is deadlock detection and recovery. Grant resource request when possible, but periodically check for the presence of deadlock and then take action to recover from it. At the fixed period or after some duration of time, we have to check, or system have to check after allocation of resource if there is deadlock condition is occur, or at the same time try to remove or resolve that problem, because this kind of problem may cause of waiting n number of processes for acquiring that particular resource. Next topic is deadlock prevention. Deadlock might be prevented by denying any one of the condition of deadlock, like first is elimination of mutual exclusion condition. This condition is difficult to eliminate because some resource such as the tape drive and printer are inherently non-shareable. The next condition is elimination of hold and wait condition. Do not allow the processes to hold any resource and request and for wait another resource. Allow only that resource which is going to release existing resource and requesting for another resource. So there are two possibilities for the elimination of the second condition. The first alternative is that a process request be granted only the resource, be granted all the resource it needs at once prior to execution. The second alternative is to disallow a process from requesting resource whenever it has previously allocated resource. Now, the next condition is elimination of no permission condition. The no permission condition can be elevated by forcing a process waiting for a resource that cannot immediately be allocated, relinquish all of its currently held resources so that other process may use them to finish their needs and that allocate to the another one. The next is elimination of circular wait condition. We have to eliminate this condition because this kind of condition possibly occur into the system. The circular wait can be denied by imposing a total ordering on all of the resource types and then forcing all processes to request the resource in order increasing or it may be decreasing order. The next topic is deadlock avoidance. This approach to the deadlock problem anticipates a deadlock before it actually occurs. This helps us prevent to our system from entering in a deadlock situation. A decision is made dynamically whether the current resource allocation request will, if granted, potentially lead to deadlock. If any allocation which is made by us or which is made by processor or which is made by operating system cause of deadlock, so do not allow that kind of allocation for any process. Require knowledge of future process request. If we have to allocate some resource, then try to know about the future request of another resources. The most famous deadlock avoidance algorithm from Dijkstra is the banker's algorithm. Two approaches to deadlock avoidance. Do not start a process if its demands might lead to deadlock. And the next is do not grant an incremental resource request to a process if this allocation might lead to deadlock. This is the banker's algorithm. The following are the features that are to be considered for avoidance of the deadlock as per the banker's algorithm. In this, each process declared maximum number of resources of each type that it may need. In this, banker says allow the number of resources which are required by a particular process, which may need and which is requested and which is required in future also. Next, keep the system in a safe state in which we can allocate resources to each process in some order and avoid deadlock. Define the ordering for allocation of resources to number of processes in that scenario. Next one is check for the safe state by finding a safe sequence, which resource allocated to which process first. Like there is a number of processes like P1, P2 until and Pn, where resources that Pi needs can be satisfied by available resources plus resources held by Pj where j is less than I. Resource allocation graph algorithm uses claim edges to check for a safe state if we are in a safe state, then we are going to allocate resources to number of processes. If any allocation may cause the deadlock state and may allow us to enter into the deadlock if we allocate that particular resource, then we are not going to allocate that particular resource at that time. The resource allocation state is now defined by the number of available and allocated resources and the maximum demand of the processes. Subsequently, the system can be in either of the following state. The first is safe state. In this state occurs when the system can allocate resource to each process in some order and avoid a deadlock, or it up to maximum allocation of resources which are required for a particular execution or for completion particular kind of task. This state will be characterized by a safe sequence. The next point is unsafe state. If the system did not follow the safe sequence of resource allocation method from the beginning and it is now in a situation which may lead to a deadlock, then it is in an unsafe state. The next one is deadlock state. If the system has some circular wait condition existing for some processes, then it is in a deadlock state. These are the limitations of Banker's algorithm. The first one is it is time consuming to execute on the operation of every resource allocation and their releasing time. Second, if the claim information is not accurate, if P1 process require only R3 and R5 resource, but our expectation and their future need according to us R3, R5, R7, R9 and 7 and 9 resources are also required by another process, but we allocate it to previous one and that is not used by previous one but they are required by the next process. So that kind of problem is occur. In the second situation, if the claim information is not accurate and system resource may be underutilized, which I told you and which we discussed in the previous example. Next is another difficulty can occur when a system is heavily loaded. When we allocate n number of resources to n number of processes, then situation is where the system is get overloaded and not handle the situations and computations related to allocation and related to release of the process and release the number of resources by the processes. Next is new processes arriving may cause a problem. Whenever a new process enter into the system, it always generates some problems, some issues related to allocation of resource, related to time, related to session which is required by that particular process for completion their task. Now the next is a resource becoming unavailable. Example, a tape drive breaking can result in an unsafe state. Deadlock detection. To detect a deadlock, we must go about in a recursive manner and simulate the most favored execution of each unblocked process. An unblocked process may acquire all the need resources and will execute that request. It will then release all the acquired resources and remain dormant thereafter. The next point is the now released resources may wake up some previously blocked processes. Continue the above steps as long as possible for prevention of deadlock or avoidance of deadlock. If any blocked processes remain, they are deadlock. Now this is the topic is deadlock recovery by process termination. In this approach, we terminate deadlocked processes in a systematic way, taking into account their priorities, their requests, their preferences. Process should be terminated based on some criterion policy. Some of the criteria may be as follows. Priority of a process. If a process have the higher priority and we are executing and the number of processes are in a queue which do not have the much higher priority, then they process have to terminate and need to terminate for execution of the higher priority process. Next is CPU time used and expected uses before completion. Next is number and type of resource being used. Can they be preempted easily? We can calculate how many resources and how much resources allocated to number of processes and number of resources are remaining for allocation and are remaining for further allocation. Number of processes needs to be terminated to preventing the system into or from entering into the deadlock situation or condition. Recovery by checkpointing and rollback. In this, about all deadlock processes, which are the causes and which are in a deadlock state. Next is backup each deadlocked process to some previously defined checkpoint and restart all processes. The first is originally deadlock may occur. Next point, successively about deadlock processes until deadlock no longer exists into the system. We are going to terminate only that kind of processes and that kind of tasks which are the causes of deadlock and which are acquiring that kind of resource which may cause of deadlock. So, by using this kind of steps, we can avoid or prevent our system from entering into the critical section problem, entering into the deadlock situation. Successively preempt resources until deadlock no longer exists. The next topic is memory management. This is the very important task in our system, in our devices, in our gadgets which we are using in day-to-day life. Memory is very much required by us for storing, for retrieving, for accessing multiple kind of data in our system, in our devices. In this, we cover the overswapping, swapping, overlays, logical memory space, physical memory space, and contiguous allocation methods. In this, we discuss about the paging, segmentations, and so on. Now start from the management of memory, and memory management is the functionality of an operating system which handles or manages primary memory. Memory management keeps track of each and every memory location, either it is allocated to some process or it is free. It checks how much memory is to be allocated to processes and it decides which process will get memory at what time. It tracks whenever some memory get freed and allocated and which one is unallocated, and correspondingly it updates the status. Memory management provides protection by using two registers, a base register and a limit register. Base register hold the smallest legal physical memory address and the limit register specify the size of the range. For example, if the base register hold 3 lakh and the limit register is 1,20,000 and something about to related this, then the program can legally access all addresses from the given range. In memory management, we have the number of processes to accessing that data, we have number of tasks for calculating the memory space and number of allocated processes task. We have to calculate how much space is remaining for allocation and how much space we have for allocation and how much space is already allocated and how much space is going to be released in how much time. Memory management provide protection. Have two kind of register which I told you just. In this, base register represent the minimum value and the limit register represent the maximum value and represent the how much space we can store into the system. Next topic is overlays and swapping. Overlay means replacement of a block of stored instruction or data with another. Overlaying is a programming method that allows programs to be larger than the computer's main memory. Overlay gives the program a way to extend limited main storage or provide a way to store the much more data as compared to the existing available space. A program based on overlay scheme mainly consists of following a root piece which is always memory resident, second set of overlays. Limitation of overlays is require careful and time consuming planning. In this we have to define how much time is required for accessing and storing the data and how much memory we have for allocation for further processes. Programmer is responsible for organizing overlay structure of program with the help of file structures and also to ensure that piece of code is already loaded when it is called. Operating system provide the facility to load files into overlay region. Now, the example of overlay, suppose total memory available is 140 kilobytes. Consider a program with 4 subroutines named read, function 1, function 2 and display. First, read is invoked that reads a set of data based on this data set value conditionally either of routine, function 1 or function 2 is called, and then display is called to output results. Here function 1 and function 2 are mutually exclusive and are not required simultaneously in memory. These number of functions help us for managing the memory and for storing, accessing this kind of information related to memory, how much space we have and how much space we can allocate and how much is required. Without the overlay, it requires 180K of memory, and with the overlay support, memory requirement is 130K. Without overlay, we have the number of functions for storing the data, like from base is 20K and upper is 40K. The function 1 overlay here 50K and the function 2 is also overlay in the same which is required the 70K. We can allow them to access in the memory by providing the overlay support into the system. Now the next topic is swapping. Swapping is a mechanism in which a process can be swapped temporarily out of main memory to backing store. Swapping and then brought back into memory for continued execution. Swap out allow to data exiting from the backing store, and swap in is a process in which we storing some data into the memory. Backing store is usually a hard disk drive or any other secondary storage which fast in access and large enough to accommodate copies of all memory images for all users. It must be capable of providing direct access to these memory images. Now in the swapping, a major time consuming part of swapping is transfer time. Total transfer time is directly proportional to the amount of memory swapped out and swapped in. Let's assume that the user process is of size 100 kilobyte and the backing store is a standard hard disk with transfer rate of 1 MB per second. The actual transfer of the 100K process to or from memory will take 100 kilobyte divided by 1000 kilobyte per second. It is the ratio is 1:10 seconds, and you can say 100 milliseconds. This is the diagram which is representing swap out and swap in. Operating system have the space for the users, and we can store the data in user space by swapping, and we can swap out from user space to backing store. This is the store, or you can say physical storage of data. If we are reading or we are picking some data from backing store to main memory, that is called swap in. If we are storing some data from main memory to backing store or physical memory, that is called swap out. Swap in and swap out are the processes where we are picking some data and we are storing some data from backing store. These processes we can represent on the basis of main memory and permanent storage, or you can say a backing store. Now the next is benefit of swapping. Allow higher degree of multi-programming, allows dynamic relocation. If address binding at execution time is being used, we can swap in different locations, in different positions, in different situations, else in case of compile and load time bindings. Processes have to be moved to same locations only. Better memory utilization, and the next is less wastage of CPU time on compaction, and the next one is can easily be applied on priority based scheduling algorithm to improve the performance. Next topic is logical versus physical address space. Logical address space is a space which is allocated on logical basis, or you can say by CPU, or that is a kind of space where you can process your task, and the physical space is the permanent storage of data, which is you can say a backing store or the physical address space. Logical and physical address space. An address generated by the CPU is a logical address, whereas address actually available on memory unit is a physical address. Logical address is also known as a virtual address. Virtual and physical address are the same in compile time and load time address binding schemes. Virtual and physical address differ in execution time address binding scheme. And the next is the set of all logical addresses generated by a program is referred to as a logical address space, and the addresses which are generated by logical addresses and which are generated by the CPU and other devices is a logical address. The set of all physical addresses corresponding to these logical address is referred to as a physical address space. Logical address space is also known as virtual address, and physical address space is a permanent storage and stored in the disk files. Logical and physical address space. The runtime mapping from virtual to physical address is done by the memory management unit, you can say MMU, which is a hardware device. MMU uses following mechanism to convert virtual address to physical address. The value in the base register is added to every address generated by a user, process which is treated as offset. You can say offset is a kind of index which refer or which link to the storage space at the time it's sent to memory. For example, if the base register value is 10,000, then an attempt by the user to use address location 100 will be dynamically reallocated to location 10,100. The user program deals with virtual addresses, it never sees the real physical address. The next topic is single process monitor, monoprogramming. In the simplest case of single user system, everything was easy, as at a time there was just one process in memory and no address translation was done by the operating system dynamically during execution. This is the way and this is the situation when a single task inside the system for execution and which is dynamically allocated by operating system. Protection of operating system or part of it can be achieved by keeping it in ROM. We can also have separate operating system or operating system address space only accessible in supervisor mode. The next topic is contiguous allocation method. So there is a kind of confusion in students, what is the continuous and contiguous? Continuous is a sequence or is a continuous statement where we know only the initial condition. We know where is the starting point, but don't know about the ending point of the allocation. In contiguous allocation method, we know the sequence is continue between the two endpoints from initial stage to ending stage, from beginning to end. We know from where the memory allocation is started and where to end. This is the chart which represents the contiguous allocation and non-contiguous allocation in memory allocation. We have the partition and two blocks, contiguous allocation and non-contiguous allocation. Contiguous allocation have single partition system and multiple partition system. It is further divided into two parts, fixed size partition and variable size partition. Variable size partition represent the dynamic or runtime allocation, and fixed partition is a static or fixed allocation. Have two types, equal sized and unequal sized inside the fixed size partitions. Now the next topic is partitioned memory allocation. The concept of multiprogramming emphasizes on maximizing CPU utilization. Utilization represents the maximum utilization of resources by overlapping CPU and input-output. Memory may be allocated as single large partition for processes to use, or multiple partition with a single process using a single partition. Single partition system. This is the approach of operating system in the lower part of the memory and other user process in the upper part. With this scheme, operating system can be protected from updating in user processes. User processes or the other processes are not able to update the processes because it is a single operating system and handled by a single in a scheme, and single user operate the number of tasks on this system. Relocation register scheme known as dynamic relocation is useful for this purpose. It only protect user processes but also from changing operating system code and data. Two registers are used. Relocation register contains value of the smallest physical address, or you can say base address, and limit register contain logical address range, or you can say the upper address range. By this ranges and by this slots we can identify how much space we have, how much space is allocated, and how much space is remaining for the further allocations. Both these are set by operating system when the job start, when the execution start. The next topic is memory management unit. This unit manages the memory and controlling the allocation of data between the range and between the available memory space. Hardware device that maps virtual to physical address. In memory management unit scheme, the value in the relocation register is added to every address generated by a user process at the time it's sent to a memory. The user program deals with logical address. It never sees the real physical addresses. In this diagram, there is a CPU which allocates logical address, like this is the 346, and the relocation register having the index value is 14,000. That must be added both of them and then allocate a physical address, that is a 14,346 into the memory. Dynamic relocation using a relocation register, and we can allow the number of process and only that memory which we have to available for allocation of number of resources. A pair of base and limit register define the logical address space which is available and which can be allocated, that is added to the physical memory offset index number to allocation of the particular memory space. This is the diagram which represents the base and limit register. Base and limit register define the logical address space like this. Limit register have this value and the base is this value. These range which can be allocated to the processes. Next is how to protect processes. Relocation register used to protect user processes from each other and from changing operating system code and data. We have some points for this, like first, base register contains value of smallest physical address, and the next is limit register contains range of logical addresses, and the next is memory management unit maps logical address dynamically. This diagram representing the way of allocation logical address space and how it matched with the physical and relocation register and what is the actual physical address inside the memory. CPU allocate the logical address and it will mapped with the limit register. If we have the logical address inside the limits, then we can allow it to access in the relocation register. Then physical address is added into this and we have the actual physical address inside the memory, and that is the address is the data address of memory. In this, we have the next topic is multi-partition. In this, we have the fixed partition in which we can store the data, like there is multiple input queue. We have the partition number of, we can store that partitions by inputting some data inside them. Single input queue is maintained for storing the data for all multiple partitions in this which we are looking, and the separate input queue for each partition represent the A block and the single input queue representing the B block. In separate input queue there is the parallel inputs to multiple blocks. In single input queue there is a single queue for every block. Every queue get the value and passing the value from this way to the number of partitions. Multi-partition dynamic partitions. Main memory usually into two partitions. First, resident operating system usually held in low memory with interrupt vector, and the second is user processes held in high memory. Multiple partition allocation have the number of blocks, block of available memory, holes of various size are scattered throughout the memory. Scattered means the memory in holes in a distributed manner. When a process arrives, it is allocated memory from a large enough hole. Operating system maintain information about allocation, about partition, about free partition, about free holes, and about how much memory is allocated and how much memory is still we have for further allocation to the number of processes. Now, dynamic storage allocation problem are the following. First, how to satisfy a request of size of n from a list of free holes. Suppose we have the number of options for allocation of memory like first fit. In first fit case, we have to store the data in a particular location where the data can be entered. We do not have to care how much memory space is wasted and how much utilization is there. In the best fit, we have to take care of everything. We do not have to store the data in that location where memory space is wasted and where the memory is not properly utilized. The next one is worst fit. We can say worst fit is a kind of allocation method. In this, we are looking for the largest enough memory for storing the data. In this, we are not going to care for about first fit, about how much space is wasting and where it is located. Allocate the largest hole. Must also search entire list, produces the largest leftover hole. Stats: first fit and best fit better than worst fit in terms of speed and storage utilization. Next is fragmentation. For n allocated blocks, another n by 2 wasted due to fragmentation. Next topic is fragmentation. There is the two types of fragmentation: external fragmentation and internal fragmentation. Total memory space exists to satisfy a request, but it is not contiguous. In internal fragmentation, allocated memory may be slightly larger than requested memory. This size difference is memory internal to a partition but not being used. Reduce external fragmentation by compaction. Shuffle memory content to place all free memory together in one large block. The next point, compaction is possible only if relocation is dynamic and is done at execution time. In that case, we have some input-output problem, that is the latch job in memory while it is involved in input-output. Do input-output. The next topic is paging. As its name implies, partition of memory into small equal size or we can say into chunks, and divide each process into the same size of chunks. The chunks of process are called pages and chunks of memory are called frames. So remember this thing, chunks of processes are called pages, chunks of memory are called frames. Operating system maintains a page table for each process, and every process have some location, have some memory address, and have the entry into the offset within the page. Every page track and every page information is stored into the memory as their information about the content, about the offset, about the location, about the page number, about the frame. So lots of information is stored into this about the pages, about the data. So this is the diagram which representing number of pages. Like we have the pages, page 0 to page 4. This is the logical memory. Inside this we have the number of frame number in which the number of data is stored. This represents the page table, and in frame we have the number of pages. We can say this is the physical memory and physical storage of data. Now the next is page allocation. In variable size partition of memory, every time when a process of size n is to be loaded, it is important to know the best location from the list of available free holes. In this we have to find the best suitable memory for storing the data in the available ones. This dynamic storage allocation is necessary to increase efficiency and throughput of the system. Most commonly used strategies to make such selections which are follows. Best fit policy, in which we are looking for the tightly memory for our data, in which very less memory is going to be waste, or in which very less memory is going to be spacious. The first fit policy, allocating the first available hole which is big enough to accommodate the new process. And the next one is worst fit policy. In this method, allocating the largest hole that will leave maximum amount of unused space. Leftover space is maximum after allocation of that memory to particular data.